Our second lesson on momentum, which deals with the idea of momentum, again, as a revision, and this new idea of impulse. Okay, so let's take an example of what we did before. Let's take a recoil reaction and see whether we can remember how to work this out. I've got a cannon and a cannonball. Let's say my cannonball is about, well, actually, 5 kilograms. And it has an exit velocity of something like 300 meters per second, maybe a bit wild, but nonetheless. And then the cannon itself, let's say, has a mass of 200 grams, and we're going to work out how fast it moves back in the other direction when that explosion takes place. So I'm sure you can remember as before. What we do is we say that the momentum before the collision is equal to the momentum after the collision. And interestingly enough here, before the explosion takes place that propels the cannonball out, there is no momentum at all. And after the collision, we have the cannonball going in one direction, 5 times 300, because it's 5 kilograms and 300 meters per second. And then we have, interestingly, the cannonball moving in the opposite direction, minus v times 200. So a little bit of rearrangement can easily sort this out. This becomes 1500, and we've moved this onto the other side, or you could say you've moved that onto the other side, which gives you 200 v. So therefore, v is going to be the 1500 divided by 200, which gives us 7.5 meters per second. So reasonably quickly, it jumps backwards. But we did all these before. We know how to do these equations, but what we're most interested in now is what type of force is exerted in that explosion. What type of force does the cannonball experience? What type of force does the cannon itself experience? And there is an equation that links these all together, and it brings about the idea of impulse. And let's just write down the equation. I'll just present it to you first of all. We say that the change in momentum is also known as the impulse of a collision or an explosion. The change in momentum, we're happy, is the mass times the change in velocity. And the impulse is the force times the time. So the force of the collision or the interaction and the time at which that force has been exerted for. So change in momentum is impulse. Mass times change in velocity is force times time. And interestingly as well, with the units here, we know that momentum is kilogram meters per second. And strangely in this case, force is measured in newtons and time is measured in seconds. They're both equal to each other. It's just that usually if we're using force and time, we mention things in newton seconds, whereas if we're looking at things in masses and velocities, we mention things in kilogram meters per second. Okay, so let's imagine now the time at which that explosion took place was 0.1 of a second. That's how long it took for the explosion to take place. So therefore, what was the force exerting between the two? Well, let's work that through. We can say to ourselves that we know that the force times the time is the change in momentum. We know, which is the same as mass times change in velocity. We're looking for the force, so we can move time over to that side of the equation, giving us force is mass change in velocity divided by time. We can take either of these. Let's work with the first one. Let's work the cannonball first. And we'll say that the cannonball is 5 times 300 divided by 0.1. And that will give us 15,000 newtons is the force exerted on the cannonball. Now let's ask, what is the force, so that's the cannonball, exerted on the cannon itself? Well, same equation. And we see that we have a 200 kilogram cannon by 7.5 meters per second divided by 0.1. If you tap into the calculator, you'll see again it's 15,000 newtons. So, first point, this is a really, really useful equation to start equating changes in momentum and the forces. And two, what I've shown you just here is that the force is actually equal. So the force acting on the cannonball is the same as the force acting on the cannon. And this is really useful. It's Newton's third law. Good. Right, let me give you an equation. Let me give you an example. Let's see if we can work it out. Let's work, because it works with any type of collision. Let's work with a snooker ball. And we're going to give the snooker ball a mass of 0.1 kilograms. Here's example one. Let's just... And then the cue is going to strike the snooker ball, which interacts for 0.05 of a second and leaves the snooker ball moving away at 1.5 meters per second. So ultimately what we want to work out is what force has occurred in that collision. However, what I might suggest we do first of all is, first part is we look at the momentum before the collision, then we look at the momentum after the collision, then we look at the change in momentum, and finally, some of these might just be the same answers, of course. Finally, we work out the force. So if you think you know what you're doing, hit pause and give it a go, otherwise here comes the solution. Okay, very straightforwardly. The momentum before, obviously it's not moving initially, so therefore the momentum before is 0. What's the momentum afterwards? Well, momentum afterwards is purely the momentum of the snooker ball. So we have the mass times the velocity, which gives us 0.1 by 1.5, 0.15 kilogram meters per second. Okay, what's the change in momentum? Well, the change in momentum is the difference between 0 and 0.15, giving us 0.15 kilogram meters per second. And therefore the force, well, we know that impulse is change in momentum. Let's write that. Change in momentum divided by change in time. Or, if that looks confusing notation, all that we said was this, which is the change in momentum divided by the change in the time. So the change in momentum we know from the previous answer, 0.15, and the time is 0.05 of a second. And that leads us to a grand total of 3 newtons, which was exerted on the snooker ball. Okay, right, let's think to another example then. Let's now think to a golf ball being struck, and I'll give you a chance to try this one again. Okay then, so we have a golf ball initially of mass 0.02 of a kilogram, if you can see that, 20 grams, and it is struck by the golf club. We can ignore the golf club's momentum, we're just interested in the golf ball's momentum. And let's say that 90 newtons of force is exerted, and it happens for a time period of 0.01 of a second. Okay, what I want to know is what is the velocity of the ball as it flies off from the golf club. Think you know the answer? Hit pause. Otherwise, here comes the solution. Okay, right. We need to work out the velocity this time. So let's start with our equation. Force times time is change in momentum. And let's rearrange it to get velocity. So in order to get the velocity, you need to move the mass to the underside of this equation here. So then that gives us change in velocity is force times time divided by mass. Okay, now we just substitute the answers in. 90 times, or the value, sorry, 90 times 0.01 divided by 0.02 gives us 45 meters per second. It's pretty fast. It's about 100. Well, it's about 100 miles an hour. So excellent. So you did that. Now the question here is, let's just take a look again at this equation. Force times time is change in momentum. Now, if you were a golfer or any type of sports star that wants to get a ball moving as fast as possible, so you want this figure to be as fast as greater as possible, for the same mass ball, you have two options available to you. You can either hit it harder, so this means talking about improving your strength, or you can increase the contact time. And the way that, for many athletes, they all have a similar strength, whereas the contact time you can increase by following through. So a follow-through of a golf, cricket, tennis, following through, though it's a large action, so this golf club follows all the way through and it actually goes all the way around until it's wrapped around there at the golfer's head again, will increase this time very slightly, but that will have a significant effect upon the velocity. Okay, let's give you another example now. We're going on to cars, car crashes. Here is my car. I'm very good at drawing these now. And it's travelling along at 15 meters per second, 1,200 kilograms worth of car. And then, that's initially, and then it strikes a brick wall and comes to rest in a mess. It comes to rest. What I want to know is, and what more information do I need to give you? Let's say that that collision occurred in 0.1 of a second. I want you to tell me what's the force of the collision. So if you think you know, hit pause and give it a go. Otherwise, here comes the answer. Okay, we know that force times time is change in momentum. What's the force? Well, let's get time onto the bottom of that equation. So force is going to be change in momentum divided by time, which gives us 1,200 times 15 divided by 0.1. And the grand total is 180,000 newtons of force. Quite a considerable force. Now, of course, this is a real life problem, car crashes. So how might you achieve a smaller force, thereby meaning anybody that's in the car experiences less force and therefore doesn't damage themselves as much? Well, let's look at another example where I just change the values a little bit. Let's say all other things are equal, but now the collision time is 0.5 of a second. Now what's the force? Well, if you want to redo the sums again, hit pause and do so, otherwise here comes the solution. Well, the force, like before, using this equation here, is now going to be the same mass of car, the same velocity, but now divided by 0.5 per second. And if you work that through, I believe you come out with something like 36,000 newtons. So you have 5 times less force in the collision if you can increase the time it takes for that collision to happen. And how do you do that? Well, you introduce a crumple zone. So I'm sure you've all seen when cars crash, just to finish off that previous video, we have crumple zones in cars, and those cars take time to slow down, and as they do so, they increase this contact time. So you'll have to describe that in words. It'll be a very descriptive answer, and what you can say to yourself, what you can say is that this is the description. For the same change in momentum for all these cars, you're assuming they're deaccelerating from, say, 70 miles an hour to stop. They've hit the wall. If you increase the contact time, then you can decrease the force experienced. And in the same way, and how do you achieve that? Well, you use a crumple zone. And/or let's imagine it's not a collision with a car, and let's imagine you're falling, you have a playground, child's playground, you introduce soft mats to increase that time. Or if you've got padded helmets, if you're cycling or motorbike, and/or even if you're in sports, use body armour for rugby, ice hockey, American football. All of those things are in effect increasing the contact time, this factor here, this denominator, and if that gets larger, therefore the force gets smaller. I mean, very interestingly, just as a last little derivation, can you see here, velocity divided by time, in effect, is the same as an acceleration. So what you're really saying is force is mass times acceleration, and you've seen that before. What are you doing by increasing the time? You're decreasing the deacceleration. So the deacceleration is smaller, so therefore there's less force. That's a subtle little extra. Okay, there we go, all done.